Okay. Okay. Because, I'll start this over. I ordered the books correctly. I went down yesterday and met with them. After we met, of course, the bookstore was closed by the time I was able to leave on Thursday. So I couldn't talk with anyone then. I was on Birmingham campus on Friday, so I couldn't talk with them then. And then yesterday when I finished classes at around 3:15, I went down to talk with them. And in one sense, he was trying to blame it on the guy it sounded like they got rid of. But I'm pretty sure it wasn't him. I kept telling him, I said, no, I think it was you I talked with. What the deal was, and I'll try to keep it short as possible. What we had were the small, what they call custom editions. The company, was real big on this a few years ago, and I said, sure, my Physical Science 111 students need these chapters, and my 112 students those chapters, so if they're not taking both courses, they don't have to buy the whole book, and there are a few chapters we don't get to, period, so they don't have to buy those, so it came out a better deal for students to do that. Well, then they quit doing it. And we went up an edition, but I said, as long as you've got them, I'll do them. Well, no one else is using them, so the bookstore kept buying them back. And then that's sort of inconvenient on the back, isn't it? The bookstore kept buying them back and reselling them, so they were making money, not a lot, but a little bit. But the students weren't having to pay as much, so we kept doing that. And last year, sometime or another, I was told they're no longer printing these, so we can't order any more new ones. Well, that's what I remember them saying, something like that. I said, okay, then I'll put on the order the big book, and this will be for both 111 and 112 because they're both in there. But it's fine with me for you to keep reselling the little ones as long as you got them. Now, here's the part that I found really suspicious about this. I don't know what happened, but most of the people who took Physical Science 112 in the fall, I had a full class of like 17, 18 students, something like that. Most of them were the other automotive students, GM, and maybe a Toyota or two in there, okay? So I doubt that many of them wanted to keep the book. I would have almost sworn to you most of them would have sold this back at the bookstore just to get a few bucks back. Not going to be a lot, but some. What they did with those, I don't know. There was certainly, I would have sworn more than one person sold it back. So what they did with the ones they had from last term, I don't know. Now that may be the guy that got rid of's fault. He may have sent those back. Who knows what he did. There's no reason for him to because we're offering the course again this term. That's the part that I think the bookstore really screwed up on. But the next place they screwed up, they didn't order the books I requested. They wound up with a bunch of 111 books and no 112 books. I had only ordered one ISBN because there is only one for this one. And I guess they made the assumption the same book was used for both courses, even though it's two different courses, custom book. They weren't paying attention. So I went down to talk with him, and he started trying to blame the other guy. I said, I really thought I remembered talking with you about it. So he went on, he looked it up, showed me that I had ordered the other one. He said, no, you ordered that one, yeah. All right, it's on me. I said, I don't care who it's on. The students have been in class for a week and still don't have a book. I said, I only know one student who has a book. Well, I've ordered 10. I said, well, there's 15 people in the class. I only know one that have a book. Okay, I'll order 14. And so he started calling the company. And here's the thing that really irritates me. He kept telling students, maybe all of you, they'll be here in 2 days. They'll be here in 2 days. Well, that book, they had to pull out of archives somewhere and print them again. And that takes more than 2 days. 2 days if they were on the shelves. They weren't. They told me before they weren't printing those anymore. So they just screwed up one way and then down the other. I mean, it's just, and he kept saying, oh, it's on me. I said, well, I don't care who it's on. The students have a test tomorrow, and all but one student has a book and doesn't have a book. So anyway, he said he was going to get them ordered, and then later I saw him. He said, "Well, I can't get the order to go through today." So I don't know if he did later in the day or what. But once he finally does it, it should be 2 days. So try again on Thursday. Hopefully they'll be here.
You said we got the test tomorrow?
Okay, no, it was today. I was telling him that yesterday, that y'all had a test today. But if you don't feel ready for the test, you don't need to take it. We'll just postpone it until you tell me, yeah, I want to take it. Now, that leads to two options. Right? What I had planned to do, thinking the books were going to be here by Friday or yesterday, and they weren't. I was planning to do the test the last 30 minutes a day, do the second lab to 2 hours before that, and then have 2 hours of class. That was going to be today. Okay, since you don't have books, if you don't want to take the test, if some of you do and some of you don't, I'll have the test the last 30 minutes a day for those who want to take it because it was assigned, and if you want to get it over with, I want you to have the opportunity. The rest of you just come back anytime during my office hours and make up the test whenever you feel like it. If nobody wants to take the test today, then I'll do 2.5 hours, just regular, of class, then 2 hours of lab. The lab will not take you 2 hours today. Okay, will not. I guarantee. Much shorter lab than the first lab. So we can go that way. So at 3:15, I'll need a reading from you whether you want to take the test or not. And again, if nobody does, we'll just continue in class until 3:45. If some of you want to take the test, then we'll stop the class at 3:15, do the lab, and then those who want to take the test do that the last 30 minutes. If none of you, we'll just continue until 3:45 as normal. Yeah. Then it'll be in class time. Yeah. Okay. It'll be the last 30 minutes of some other class period, not today. And we'll have plenty of opportunity for that. So you don't have to tell me now, but at 3:15 I'll need to know. Now, I hope I said this, and maybe not everybody was here to hear it, but let me say it again. For every test, even including the final, you can have a formula and equation sheet. Anything you want to write down on a piece of paper, you can have. Front and back, as small as you want to print it that you can read. Anything you want to write down on a piece of paper, you can have. Okay? And then you can use scratch paper calculators, whatever. The first test, remember, is a few more calculations that you'll see on any other test. Okay? Most of the other tests will be multiple choice. There are a few multiple choice on the first ones. But most of the other tests will be mostly multiple choice, maybe 1 or 2 calculations, and maybe 1 or 2 fill in the blank. Okay? The first test, several calculations, several fill in the blank, and a few multiple choice. Yeah.
How many questions is usually on the test?
Usually around 20, usually less than 20, but I shoot. Most of the time I shoot for 2 pages, and if they're multiple choice, they take room, so it's going to be something close to 20 questions. Never more than 20, sometimes close to 20. The first test, though, has a lot of multiple parts to it, so it's only 10 questions. So it's only on 1 page, 10 questions, but there's many with multiple parts. So there's a total of 17 possible answers or something like that because it's multiple parts and so on. Okay? So, just let me know. Now, I also remember that we didn't quite finish the lab from last time, but like I said, the lab today is very short, so we have plenty of time to finish the last lab. There's no more measurements to be made, just to make sure y'all have all your questions answered. And then, once you have those done, we'll start the next lab. But all that will be in 2 hours, and it'll be done well before 2 hours. I'm sorry?
Said that we turn the worksheets in.
Yeah, when you're finished with them, you turn them in, right. The labs, right. Okay, any other questions? Okay, where we left off last time was bottom of page 27, or at least in my book it is. Sorry that y'all don't have them. Sometimes in the past I've had a couple of old editions of this, but other students have taken those and not returned them, or that was fine with me because I had no more use for them. But I don't even have any more of the older editions of this anymore. So, but remember, everything that we've done so far is out there on YouTube, so you can use that to study for your test as well. All right, any questions on anything before we get going? Picking up again with chapter 2. Yeah.
Everything that we discussed in class, that's what the test is about. There's no extra stuff that's in the chapter that might be in the test. Is that what you're saying?
I can't remember any questions that are on the test that we haven't done something similar to in class. It may have been very short and in passing, but we have done it. It always helps to read the book too, though. I always say this, but y'all don't have the book, but then to go over this. But once you get your books, to read the books, that will be helpful in addition to what we do in class. The PowerPoints cover most of it. Anything that's not specifically on the PowerPoints, I try always to say. But my memory of what's on the test is not always, may not remember it all. But this first test, I'm pretty sure we've gone on everything that's on there. Okay. All right. Any other questions? Yeah.
This is the only class that is physical science 112. Because you said he ordered books. That means they are reserved for us only.
Yeah. There's no other physical science 112 course, right? There's 111. I taught the first mini term, 112 second mini term. And in the past, at one time they had an instructor they were assigning the physical science class to on the Birmingham campus, but she hacked off the department chair, so she was an adjunct, and they didn't hire her back, so they're not offering it on the Birmingham campus anymore. That's why there's no books over there. But I barely can fill. I offer this second mini terms fall and spring because that's when the automotive programs need it. So that's why it's offered now, and everybody else can take it too. And because y'all need it second mini term, I always offer physical science 111 on first mini term. The fall, the 111 didn't make, but this term it did. And in summer, I offer both of them, but quite often one or both of them don't make. So, but they're always offered. So most of the time, it's you guys, either the GM, Toyota, or Ford, and then other students who want to take it too. So these almost always make second mini terms fall and spring. All right, any other questions? All right. We had talked about measuring motion and various ways of talking about motion, and one way, of course, is speed. The definition for speed is change of position with respect to time. Okay? Another way to say that, the time rate of change of position. In other words, how does position change with time? Now, there's two types of speed. There's the average speed, and these are the ones you commonly measure. For instance, my wife and her sister took their mom to New Orleans over the weekend. Okay, it was her 80th birthday present. So they went down there, and I'm sure, knowing Karen, she probably did mental calculations in her head, about, well, we got this far to travel, and it's going to take us about this long. What will be or what will I average the speed? How long will it take till we get there? So quite often you deal with average speed. Okay, the most common of the measurements. However, the instantaneous speed. Now before we do average speed, here is speed is distance over time. So when you're talking average speed, that's change of displacement or distance. Okay, change of position, change of displacement, distance, all meaning of it the same, over the change of time. And I think the earlier slide that we showed in last time had an example of that. No, I thought there was going to be another. Well, wait a minute. This was the last slide, sorry. Yeah, that was the one that showed it. I hit the wrong key. Okay. No. Okay. I'm going to show you the way I commonly refer to this. You'll see it in the book some, but here's another way of saying this. Well, let me get my pen color changed. Okay. Average speed. Okay. Now the book uses the word speed, and I don't think they do a symbol. This equation is on the next page. To do average, they usually put a bar over it. Okay, now don't confuse that. If this had a point on it, as in an arrow, that means a vector quantity, meaning velocity. Without the arrow, that's an average, and without the vector, it's not velocity, it's speed. So sorry we're using the same symbol, but remember the magnitude of the velocity is the speed. Those are usually interchangeable. Now, in the book, they use this symbol, just like you saw in this. Speed is equal to distance over time. This is average speed is equal to, the book says, distance over time. Now that's what I call the parameter equation. You just use a single letter to stand for your various quantities. And this is one of those things you can do like a triangle or circle. Remember, distance on top, velocity and time on the bottom, and speed and time on the bottom. Okay? Now, here's how I like to do it a little more precisely. Change of displacement over change of time. Now that little ugly looking shape there is supposed to be a triangle, which is the Greek symbol for delta, capital delta anyway. And that means difference in. The difference in the position over the difference in time. And the next example will show this, and actually the previous example did. So, what do we mean when we're talking about instantaneous speed? Well, that would be when this time interval is getting smaller and smaller and smaller. For instance, when my wife went to New Orleans, drove to New Orleans, what did that take? Maybe 6 hours, something like that, about, if y'all have done it before. What if she was talking about, no, how about just here to Tuscaloosa with no stops? Then that would have been a shorter interval, but it's still an average speed because it's covering quite a bit of time. That could have been maybe 1 hour, hour and a half, something like that. Well, what if you say, no, I want it's even shorter than that? Well, here to the end of the road. That's still an average speed because it's taking a definite time interval. But when that time interval is being reduced smaller and smaller and smaller until it's at the instant, of course you can't divide by zero, okay? So that's where calculus comes in. Don't worry, you don't have to have calculus for it. But basically your instantaneous speed is the speed at a given instant. And it's what they call the limit as that time interval gets smaller and smaller and smaller. So then we talk about the speed, and I won't put the average over it because it really isn't. That would be distance over time, and that would truly be instantaneous. Now, they say the most common measurement is the average speed. It depends on who's doing the measuring. If you're on the highway and the guys or gals with the blue lights on top, okay, most of the time they've got a device that's really registering this. So don't even try it. Well, it may be worth the effort, but I don't think it will work. Say, oh, but officer, my average speed was much less than that. You know, don't think it'll work, okay? So I wouldn't even suggest trying it because they're interested in instantaneous speed. Oh yeah, I had stopped back there for lunch, so my average speed was way less than that. You know, not going to work, I don't think. Okay. All right. So here's an example of average speed, very similar to the one we had before. Initially, you had traveled 50 kilometers in 1 hour. Anyone want to make a guess of how fast you've been traveling? 50 kilometers an hour, very good. And then the second hour, you traveled another 50 kilometers. and still at 50 kilometers per hour, and the other you traveled another 50 kilometers, and that was another averaging 50 kilometers per hour. So calculate the average speed between the trip time of 1 hour and 3 hours. So from here to there, what was your average speed? I think we all know it, but let's do the calculation. What is the formula for average speed? V bar is equal to change of distance over change of time. Now, this gives me another thing. What do we mean by change of or delta, the difference? Okay? It's always D final minus D initial. Always final minus initial. Okay? Over T final minus T initial. Okay? What was your final displacement? 150 kilometers. Minus the initial displacement? 50 kilometers. And what was the final time? 3 hours minus the initial time? 1 hour. Okay? They've made this one really easy for you. Okay? And this would be what? 100 kilometers divided by 2 hours, which would be 50 kilometers per hour. Okay? Now, do most of y'all usually travel around 50 kilometers an hour? Huh? I know you usually don't, but let's think about it. Is a kilometer longer or shorter than a mile? Say again?
It's like 28 miles an hour.
Yes, it's really, so I don't think most of you do. Right? Well, I couldn't say that. I shouldn't even imagine it. So, does that mean the whole time necessarily you're going at 50 kilometers per hour? Or maybe you stopped and made a pit stop here. Maybe you stopped and, had lunch or a snack or something here. Probably not lunch, but a snack or something. So yeah, you could have been doing any kind of speeds in between there, but you only traveled 50 kilometers in that hour, and 50 kilometers in the next hour, making 100 kilometers in 2 hours, so your average speed was 50 kilometers per hour. Now, if that would have been in city driving, with lots of lights and stuff, yeah, you could have been averaging 50 kilometers an hour or less, okay? Open road, probably not. I'm making a guess. What's that?
If you're driving that slow on the highway, you get to
Yeah, you sure might get in trouble then. All right, now, let's go back to the formula. There it is there. Oh, let's do this one. Okay? Now, just like I said before, well, let's see, I don't need that. Okay. Just like I said before, you can come up with 2 other equations based on that one. Can anyone name what they would be? Second? Okay, you want to solve for time? What were you saying? Okay, which one you want to do first? Say again? Okay. Okay. The only reason I'm going to go against you is because you got to do the other one first anyway. First thing, let's go for distance. How would you get distance? Yes, multiply both sides of the equation by time. And that, then, the time would go out here, and you'd have distance is equal velocity times time. There's the second equation. Now let's do the time one. How do you solve for time? Divide by velocity. You got it. The velocities go out now, and you get time is equal to distance over velocity. Okay? Or you can use your circle or triangle and just do them hardly without thinking about them. Really, it's a good idea to think. Okay? But you do. But on the other hand, always use your units, because if your units don't come out right, the odds are you've done the problem wrong. So your answer's probably not right either. Okay. So, anytime you get one formula, you can usually get 2 or 3 or so others out of it, 1, 2, or 3, so many out of it. Okay, let's do example. Now, again, I've sort of scrolled through here. Okay, let me back up. Okay, I'm going to clear the ink here because they do show something here. Yeah, here's the formula that you use. Average speed, see they use that one. Average speed is equal to distance over time. What are the distance and time? Well, they don't show, but we calculated them, okay? The change of displacement was 100 and change of time was 2. So 100 divided by 2 was 50. Okay. What they don't show, and I really wish they did, was the figure, and I know y'all don't have the books, so rather than me trying to draw it, I'm just going to put it up here. And it's a pain in the neck too, but okay. Now this doesn't get recorded, okay? So you see it, people at home don't. Here they show a graph of this, and y'all liked doing your graphs last time, I could tell. And don't worry, every lab just about comes out of the lab book. They have graphs of them. Maybe not everyone, but most of them. The one we're doing today is not out of the book. It won't have one. I'll show. Okay. But here's your distance over time. So the slope of that line is going to be your velocity. You got it. Okay. So get used to seeing graphs, having problems. We don't have any problems. Most of the time, yes, it will be. Yeah. And that graph, especially since it was a straight line, that tells you immediately you're going at constant speed. Okay? You're traveling the same distance for every time interval you go. Most of the time, it's not. You're going, like this all the time. When you're driving, you're speeding up, slowing down, stopping at lights, getting behind the truck, it's changing all the time. Now, if you had a graph that was curving like that, average speed would be, given a time interval, how far did you move? Change of distance over change of time. On the instantaneous, once you started taking smaller and smaller increments, you can imagine that line, as you follow the curve, is going to be changing slopes all the time until it goes down almost to 0, and then that's your instantaneous speed. And that then would be instantaneous. So most of the time, you can't do that. Now, once you, hopefully some of you, I doubt if you will, but if you ever went as far as calculus, that's what calculus calculates the instantaneous speed. That's with derivatives. That's beyond the scope of this course, so we're not going to do it. In fact, that's probably the only time I ever mention it. Okay. What's that? Oh. Yeah. Good stuff, isn't it? Yeah, I could tell you're enthused about it. All right, so one of those formulas we just came up with before, like this one, distance is equal to velocity times time, they do a little example with that one. So if the V bar is equal to 50, this time they're doing kilometers per hour still, and you traveled 2 hours, so your T, or delta T, was 2 hours, how far did you travel? Pretty easy. 100, because you multiply 50 kilometers per hour times your 2 hours. Hours cancel out, and that leaves you 100, and since hours cancel out, kilometers, and that's a great unit for distance. Okay? So units are your friends. Okay? Don't disregard them, and if they don't cancel out properly, you're probably doing the problem wrong. Okay? A lot of times I don't know if you'll hear me say it or not, but most of the time I try to say it. I don't ever like to talk about canceling numbers out. I divide out numbers. But with units, you literally cancel them out. So keep up with that. Now, if they had given this as 20 minutes, then you can't do this. Even though that's the time and that's the velocity, the units don't match. So then you either get your hours here to minutes or get those minutes to hours. And then do your multiplication. So always make sure your units are correct. Otherwise, you're going to have some pretty serious errors. Right. 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 Then you cancel the foot here with one of the feet here, leaving your foot on top. Yeah. That would be like if you were saying this room has, I don't know, someone give me a good idea, 80 square feet, bigger than that. I know, count the tiles, I just haven't counted on. Yeah, okay. Whatever it is, divide that by the width, and that gives you the length of the room. And that would be in feet. So the square feet divided by feet would give you feet. Yeah. That would be an example of what you just said.
I think we had divide some units in our lab.
What's that again?
We had to divide in our lab.
Yeah.
We had to divide.
Yeah. And you hang on to the units. Most of what I remember that you were doing, now when you had things like cubic centimeters in one place and milliliters in another, the question said, what do you get there? And then that would be so many milliliters per cubic centimeter or cubic centimeters per milliliter. Even though they're measuring the same thing, that's what you were gunning for. You were trying to find out what that conversion was, and it should have come out, and I think I saw most of you, it did come out pretty close to 1. That's what you expected it to, okay? Density of water was grams per cubic centimeters or gram per milliliter, and that should have come out pretty close to 1 because that's what the density of water is in the SI unit. So I don't remember that we were canceling many units out. We may have been, I just don't recall. Those on the blocks, you had square meters or square centimeters divided by cubic centimeters, so that left you with 1 over a meter, which was a weird unit, and I told you could just leave that off if you wanted to for that problem. Okay, so yeah, you did run into that. We also have here an example 2.1 and 2.2. Let's do those. Okay, okay, hit the wrong button. Okay, 2.1, the driver of a car moving at 72 kilometers per hour. What is 72.0 kilometers per hour? What does that represent? Okay, but the whole unit, 72 kilometers per hour. That's the speed. Okay, the symbol we usually use for that is V, and probably V bar, because if you read it carefully, it says, well, no, it doesn't. It says has the speed of that. Okay. Now, most of you here last time when I went over this, why did they put a 0.0 there? 3 significant digits. Okay. That's just 72, but you measured it to the nearest tenth of a kilometer per hour, so you put the extra digit there. Okay, that helps you know how far to take your answer. Okay, so the next thing it said here, and the time factor is 3.00. Boy, that's precise, isn't it? Seconds. So that is your time. Okay, the question said, how far, okay, I'm sorry, I'm not reading the problem. The driver of a car moving at 72 kilometers per hour drops a road map on the floor. If it takes him 3.00 seconds to locate and pick up the map, how far did he travel during that time? Okay? So what are we looking for? Exactly. But what are we looking for? How far did he travel during that time? What are we looking for? What will answer that question? Say again? How far? What question does that ask? Distance. So that's what you're looking for. The distance is your unknown here. And you're very correct in saying, here you have hours, there you have seconds. Whoa, folks, you got to get the same units. So I'm going to show you how I like to convert units. If you have a better way that you like, you're familiar with, and comfortable with it, do it. Here's what I suggest, though. Okay? And sometimes doing this, you don't even have to use your formulas, but we'll get there in a minute. Let's take the 72 kilometers per hour, and we're going to multiply that. I'm going to do it a couple of times, and I want to change that. And by the way, since we're doing kilometers per hour, that's a long distance over a long time, and your question here is how far. Do you think you're going to give me that answer, how far you traveled in 3 seconds, in kilometers? Probably not. What unit do you think might be a better unit? Second? Meters. Yeah, okay, let's do meters. So we might need some more conversion things here, because we want to not just change your hours to seconds or seconds to hours, but we also want to change our meters, kilometers to meters. So I'm going to do one more, and that's going to equal so many meters per second. If we get our velocity in meters per second, then we can use our 3 seconds. Right? All right. I'll let you choose. Now, what have I done here? I put that's a dot for a multiplication, 2 blanks, another multiplication, another. These are conversion factors. Conversion factors consist of numbers, that's why I put the first block here, and units. That's in the second block. Numbers, units, number, unit. You have top and bottom, top and bottom, top and bottom, numbers, units, numbers, units. Now, my suggestion to you, this is how I like to do it, always put the units in their place. Okay? Start with the units, then match the numbers with the units. So, which do you want to do first? You want to mess with kilometers to meters or hours to seconds? I don't care. It doesn't really matter. Hours to seconds. So, does anyone happen to know the conversion unit from hours to seconds or seconds to hours? Okay, you're doing minutes, aren't you? So let's do an intermediate one for minutes. Let's first get the hours to minutes. So put the units into place. One goes on top and one goes on bottom. Which goes where? Goes where? Okay. Just tell me what unit goes on top and what goes on bottom. Between hours and minutes, which will go where? Say again? Okay, you want minutes on top and hours on the bottom? When you go to multiply this, you're going to wind up with kilometer minutes per hour squared. Does that sound reasonable? I don't even know what a square hour is. Okay, I'm guessing not. Nothing canceled out, did it? That's why I say always put their units in their place. So let's not do it that way. How might we want to do it? Okay, say again. Okay, that's okay. What unit goes where? Something on top, something on bottom. Yeah, put hour on top, minutes on the bottom, and this way the hours are going to cancel out. You see? Okay, now you match the numbers with the units. How many hours in a minute or how many minutes in an hour? You know that one, don't you? Which? 60 goes with the minutes, 1 goes with the hour, right? There's your first conversion. This will now give you kilometers per minute. Okay, you want to continue with the time to get minutes to seconds, or you want to go back to get kilometers to meters? I don't care. Again, it doesn't really matter. You name it and claim it. Second? Minutes to seconds. So again, which do you do first? Units in their place. What unit will go where? Minutes up top, seconds in the bottom. That cancels the minutes out and leaves seconds just where you want them, on the bottom. Okay? Now, again, I ask you, match the numbers with the unit. How many minutes in a second or how many seconds in a minute? 1 minute is 60 seconds. You got it. Okay? One more now. You need to get kilometers to meters. What goes where? Okay, you're doing the numbers. Let's give me the units first. You're right, but give me the units. Huh? Say it again. Meters in the numerator and kilometers in the denominator. Why? So kilometers cancel out, and that leaves meters where you want it, in the numerator. Right? And now you tell me how many meters in a kilometer or how many kilometers in a meter. Match the numbers with the units. 1,000 meters is 1 kilometer. Okay? Now, if you got a calculator, you can use it. If you don't, it's still not very hard to do. I can wipe out 2 zeros right there, and that'll get rid of 2 of those zeros. Okay? I can do 6 into 72. That'll go 12 times. I'll do the other 6 into 12, and that'll go 2 times, and that gives me 20 meters per second. Or you could use your calculator and got the same thing. Maybe taking you a little longer, but not too bad. Okay? 20 meters per second. That makes sense? Okay? So if you're going at a speed, that's the same as 20, and that's actually 0.0. Yes, meters per second. Now we can use our formula. What's the formula for distance that we came up with a short time ago? V, average velocity, that shouldn't be an arrow there, average velocity times time interval, okay? And that would be 20.0 meters per second times 3.00 seconds. And what would that give you? 60.0 meters, because the seconds again go out, okay? Now, 60 meters, how far is that? Approximately. Any of you ever been to a football game? Ever in your life? Seen it on TV? It's a little more than 60 yards, probably close to 65 yards. So you're driving along at 20 meters per second, 72 kilometers per hour, drop the map on the floor, pick it up, 3 seconds later you come up, you've traveled more than half a football field. Basically about 2/3 of a football field. That's quite a bit of distance. That's one reason you don't tailgate. Because what in those 3 seconds, if the guy ahead of you had slammed on brakes, you've already got a bumper in your face, okay? Not a good thing to have, okay? So yeah, you've traveled 60 meters in those 3 seconds. Make sense? See how to do those? Okay. Now the book has a sort of a strange way of doing it. They got the same thing, but boy, that looks so convoluted to me. Okay? To me, the way I did it makes a little more sense. You might like the way the book did it, or you may have another way of doing it you like so much better. As long as it's right, do it that way. Okay? Now, very similar problem. Oops, hit the wrong key. Example 2.2. A bicycle has an average speed of 8.00. Boy, these are really precise measurements, aren't they? Kilometers per hour. What symbol do we usually use for that? So, say again? Yeah, V bar, average speed. Okay, and in fact they said average speed, so that is definitely V bar. How far? So what are we looking for? Distance, that's your unknown. Will it go, travel in 10 seconds? What's 10 seconds a measure of? Time. I like to call it delta t, but we'll leave it as t now, that's fine. Again, you're in the same situation. So what do? Start with your 8.00 kilometers per hour. And you got to do some conversions here. And you want to wind up with meters per second again, because you got seconds here, and you want a shorter distance, so I think meters would make sense. How would you do this? Okay, kilometers on the bottom, that'll be fine. What would go on top? Meters. How many meters in a kilometer or kilometers in a meter? 1,000 meters in 1 kilometer. Got it. And your kilometers cancel out. Next. Okay, do the time part. What goes where? Hours in the numerator, minutes in the denominator. What numbers match those? 1 hour is 60 minutes. Very good. And by the way, these are exact. You can put as many decimal and as many zeros as you need. I'm not writing them in, but you could, okay? Because those are exact measurements. That gets rid of your hours. Now you're left with meters per minute. We want meters per second, so what do we do next? Minutes in the numerator, seconds in the denominator. What numbers match there? 1 minute is 60 seconds. Very good. Now the minutes go out. They've been dating, okay? And you're left with meters per second, okay? Now this one won't be quite as nice as the last one. You can cancel out the 2 zeros, so that wipes out those 2. And then you can go, 2 will go into 6 3 times, 2 will go into 8 4 times, 2 will go into 6 3 times, 2 will go into 10 5 times, and that's going to give us 20 over 9. Calculator time. By the way, on the test, since there's going to be a lot of calculations, be sure you bring your calculators, okay? If you don't have one, they have them pretty cheap, I think, in the bookstore, probably even cheaper at Walmart or Office Depot, those kind of places. If anyone got a calculator, what's that?
I think you get like $10 in the.
I bet so. That's pretty cheap. And I think I put on the book order that they are required for the course, so if you want to buy them on Pell Grant, you can. Okay, so you don't have to shell out any bucks for them. So anyone do it? Or can you just do that in your head? It's not that bad. 2.22. Now, in this case, you might want to go an extra 1 or 2 because you're not through with the problem. But I think we're okay with it. 2.22 meters per second. I stopped at 2 because we had 3 significant digits there, 3 significant digits there. Okay? Now, what's your formula for distance? Average speed times time. Your average speed you just calculated to be 2.22 meters per second. Multiply that by 10 seconds, 10.0 seconds. And what does that? The seconds go out. That gives you 22.2 meters. So in 10 seconds, he'll travel about 1/5 of a football, close to 1/4 of a football field. Near 25 yards, 22.2 meters, pretty close to 25 yards. Okay, but he's going much slower, 8 kilometers per hour. All right, does that make sense? And you notice their answer in the book is 22.2. Your calculator, if you kept all those digits on there, it would say, here it would say 2.2222222222, you know, as many digits as you have on your calculator. You don't need them all. You look and see, I only need 3 digits. Now in the intermediate calculation like that, you might want to keep a 4th digit, but then at the end, round it to 22.2. Don't give me a whole string after that. Your significant digits tell you when to stop or how far to keep going. Okay, there are a couple of concepts applied. One is style speeds, which I think is sort of nebulous, but if you're interested in that, read it. The other, how fast is a stream? That's a sort of an interesting little problem. And people who study this kind of stuff, they'll actually do things like this. Say, drop a leaf, measure a fixed distance along a stream with a tape measure, and have one person at this and drop it on, starting a stopwatch, and when it comes to the other end, stop it. You know the distance, you've measured the time, you'll see about how fast the stream is flowing. And for people who are studying ecology and that kind of stuff, that may be of interest. So you'll see these little blurbs. Sometimes they're worthwhile, sometimes they're just sort of, okay, fine. Okay. Like style speeds, that's a okay, fine one. Okay. So what? Okay. Let's move on to velocity. What's the difference between speed and velocity? Anyone remember from last time? Speed is the magnitude of velocity. A good way to put it. What does that make velocity? If speed is just the magnitude or the size or the amount of velocity, what does velocity have? Speed doesn't. Say again? Direction, exactly. Velocity is speed with a direction. Okay? Velocity describes speed, how fast is it going, with the direction, where is it going, which way is it heading, okay? That is the difference in speed and velocity. And I gave you the technical names for this before. Something with magnitude only is called a scalar quantity. Speed is scalar, SS, okay? Velocity, something with directions, are called vectors. Velocity vector. It just happens to be with this relationship, the letters clue you in pretty well. Okay? The graphical representation of a vector, which is magnitude and direction. The length represents the magnitude, the arrowhead indicates the direction. Okay? Now when you're just writing them along. Okay, say this one more time. I hear you.
You said it says vectors like plural, like there's more than just one type of vector.
Oh yeah, I mean anything. Velocities are vector, accelerations are vectors, forces are vectors. Lots of things are measured in vectors. Right. Things that are measured in scalar only. Time. Time has no direction. So no Back to the Future stuff. That's science. That's fiction. Not even science fiction. That's just fiction. Okay. Mass is just how much of it is there. Okay, so some things are only scalar quantities, and speed is only scalar, but many other things are vector. By the way, energy, work, those are scalar quantities, not vector quantities, and we'll see those when we get closer to them. But yeah, several things that represent vectors. Then you can have a velocity vector here and another one here. So those you can have two vectors of the same quantity. And then you have to add them as vectors, not as scalars. Okay. Did that answer your question? Yeah. So here's an example. This car up here is going 30 kilometers per hour to the east. Most of the time we do to the right is east, north is up, west is left, and south is down. So this is going 30 kilometers per hour to the east. This one down here is going 60 kilometers per hour to the east. So we take this 30 and double it. Looks like close to doubling anyway. That means a larger magnitude but the same direction. So definitely not the same vector. Because this one longer. This is going the same length here, but this one's going 60 kilometers an hour northwest. So same speed, different directions. So even though the speeds are the same, the velocities are not. So velocities can be different even when speeds are the same, because speed is just the magnitude. Make sense? All right. Boy, that was all for velocity. One paragraph in the book. Let's move on to acceleration. Okay? Anytime you see the word rate, you know there's going to be another division in it. The rate at which motion changes over time. That's one definition. I don't really like it. I prefer the rate at which velocity changes over time. So whereas velocity was change of displacement over change of time, okay, acceleration is change of velocity over change of time. So in this book, and in most physics books, when they say motion, they usually indicate or imply velocities. Because if something's moving, it's got to have a velocity, right? So the rate at which motion changes over time. So that will be change of velocity over change of time. Now, three things can cause accelerations. Okay? So I'm going like this. And speed up, my velocity, my speed is changing over the time period. So therefore, I'm accelerating. Right? Is this an acceleration? Your direction is changing over time. Why is that an acceleration? Even if you're going at the same speed. Because the motion is changing. The velocity is changing. Velocity is a vector quantity, and if you're changing direction, you're changing velocity, even though the speed is fixed. Okay? So when you go around a curve, even if you're at constant speed, you're accelerating toward the inner part of the curve. Any of you ever experienced that? Or lack of that? Go around the curve a bit too fast, faster than the tires in the road, or the slickness of the road, or the cant of the road can handle, you're into the ditch, or you're getting close to it. Okay? Think of your racetracks. Straightways, they're like this. On the curves, bank like this. Why? Well, yeah, you're needing the road to push you back in, to accelerate you toward the center. Otherwise, over the top. They'd have to slow down like crazy going around there, because the tires just cannot accelerate you well enough. So, yeah, if the distance is changing, you're guaranteed to be accelerating. Or you can be changing both speed and direction, and that is also an acceleration. Can acceleration ever be negative? Sure. I started fast, ended slow. Remember your delta, final minus initial. This was 3 meters per second. That was 10 meters per second. The change was a negative 7. However many seconds it took me to do it. So yes, acceleration can be negative. Now we sometimes call that deceleration, but in physics we call it acceleration, but just make it a negative number. Okay? Just like velocity can be negative. If I'm backing up, negative velocity, right? My initial is here, my final is there. That's negative compared to this, so yeah. Okay. Here's the examples of that. The car started at 30 miles per hour, ended at 60 miles per hour, definitely was accelerating, right? Car started at 60 miles per hour, ended at 30 miles per hour. Acceleration? Yes. What can you tell me about acceleration? Negative. Yeah, it's a negative acceleration. Here it's 30 miles per hour, there it's 30 miles per hour. Is that accelerating? Yes, it is, because it changed its direction. Your velocity was changing not in magnitude, but in direction. Therefore, it was an acceleration. And this one, 30 miles per hour up here, 60 miles per hour down there. Yes, both the direction and the speed was changing. It's a pretty compound change of acceleration. Okay? Make sense? Okay. Now, what would we mean by uniform acceleration? The acceleration is not changing. Constant, straight line. Why does it need to be straight line? You got it. That's changing your acceleration, because acceleration is also a vector quantity. So constant speed, constant magnitude acceleration, straight line acceleration, that's what would mean uniform. Not changing the acceleration. You think the velocity is changing? It's the acceleration that's constant. That's sort of a trick question. If that acceleration was a constant 0, no, the velocity isn't changing. But if that acceleration was constant anything else, positive or negative, your speed is changing. The average velocity is related to initial and final velocities in this case, if you have uniform acceleration. In the lab we'll do today, we're going to have uniform acceleration, or at least assume that, so your average velocity can be calculated a different way. Okay, let's say after 2 tests, I say, what's your average in the class? How would you tell me? Add the 2 together, divide by 2. So when you have uniform acceleration, in other words, constant straight line acceleration, then another way to get average velocity is do your initial velocity plus your final velocity divided by 2. That will give you, that's another way. So we have 2 ways to get average velocities now if you have uniform acceleration. What's the first way? Average velocity. Now I'll put an arrow over it and a line. Average velocity is change of position over, or distance, you could use distance, over time. That's one way. The way we just found out here, average velocity would be, what does it say? V initial plus V final divided by 2. So we'll use both of those equations in today's lab. This will be the one you'll use first. Later you'll use this one to solve for final velocity. So be ready for that to come upon you. Okay. There we have it. Almost written as pretty as mine. Average velocity. Now, they didn't indicate its velocity. They have its speed. Either way will work. Final speed plus initial. It doesn't matter. When you're adding, it doesn't matter. When you're subtracting, it matters. It's always V final minus V initial. That's your delta V. But when you're adding, it doesn't matter the order. Okay. Addition is commutative. Remember that from math. And subtraction is not commutative. The order matters in subtraction. Average velocity, add the 2 together, divide by 2. This is the way we did it a couple slides ago. This is another way to do it. Make sense? All right. Wow. I got through that in a hurry. But there are a couple of examples. Let's pause and do those. One is not listed as an example. They just do it. So let's back up here. The strange thing is, in the text, they talked about it, but they never actually gave you your, they gave you the definition here, but didn't give you the formula. I'll give you the formula. It's very much like velocity. Acceleration, we'll use A. I'll put a vector over it because most of the time it is change of velocity over change of time. Now, it was probably several years ago, and it was about final exam time in this course, and one of the students said, "What does that delta mean?" And we have been using it all term long. So is this delta confusing, or is it making sense to you? I don't want you at the end of the term say, "Well, what does delta mean anyway?" I mean, this guy did, I'm glad he asked, but the thing is, I thought, why didn't you ask this earlier? Delta means change, difference, delta, difference, change in. And so what would be the way to express this? Difference between what? Yes, final velocity minus initial velocity over your time interval. And you can usually put T. That is a delta T, but you could put it as T final minus T initial. Okay? For instance, my wife's trip last weekend, okay? If she left at 9 o'clock in the morning and got there at 3 o'clock in the afternoon, T final would have been the 3 o'clock, and T initial would have been the 9 o'clock. You probably would have put it in military time. That would be 1500 minus 900 would be 6 hours, or something like that. Okay. So always final minus initial. Okay. Notice velocities and accelerations are vector quantities. Time is a scalar quantity. No symbol for it. No symbol over the top. Okay. So can you give me two other equations you could get out of this equation? Okay, and what would that be? Delta V would be acceleration times your change of time. Perfect. Now, quite often they'll say that V is equal to AT. They won't use the deltas, but you understand it is an interval. And your other one would be? Delta T would be? Delta V, I forgot my, over delta A, right? You would divide both sides by A. And you don't need a delta on the A, sorry about that. Okay, was there a question? Okay. Yeah, okay. Okay, these lines here are vector lines. They've got a point on them. And I'm not putting two sets of lines there, but yeah, that is an average velocity, okay? I mean average acceleration, because it's over an interval. Change of velocity over change of time. If that change of time had reduced to 0, then that'd be an instantaneous acceleration. Then you really only need the arrow over it. You don't need the bar. I just haven't been writing bars and arrows both. That is, you're right, that's the average. Both of those are averages. Right. What's that? Yeah, the book usually doesn't put them. Sorry.
Your unit for acceleration is going to be like...
Ah, very good. Let's mention that. What is it?
It's like a ratio, right? Like, say, 10 miles per hour per so much distance.
Not distance. Time. So, yeah, that's one way to do it. In fact, when you're talking about how hot your car is, what do you usually say? I can do...
120 miles an hour.
Say again?
120 miles an hour.
Okay, that's just how fast it is. But what's even more impressive? I can do 0 to 60 in 2 seconds. What is he meaning there? 0 to 60 is what? Okay, he's talking about acceleration, but 0 to 60 is what? Change of, no, 60 is your speed. From 0 speed, is stop to 60 miles an hour in 2 seconds. Yeah, right. Okay, dream on. Slap yourself, wake yourself up, you're dreaming. Okay, never mind. Okay. What you've just described is an acceleration. Because you do it 0 to 60 miles per hour. That's probably what you meant, right? In so many seconds. Change of velocity over time. So that would be your delta V over delta T would be 0 to 60 would be 60 miles per hour. I'm just going to put MPH. It's easier to write. Minus 0 MPH. And then you started from a dead stop in 2 seconds. Yeah, dreaming. Okay. That would be, and what would be your units? That would be 30 miles per hour per second. That is how you would refer to that. Now, most of the time what we're going to be doing in the lab, in fact, today we'll be doing it, we'll be measuring everything in terms of seconds. We're not going to be going so many miles in the lab today. It's going to be that. So quite often, something you'll see like in the lab today may be something like, let's just use 30 again, 30 centimeters per second per second. Now there's a shorthand we use there. Anyone know what that would be? 30 centimeters per second squared, yeah. I don't know what a square second is, but that means second per second. Okay? Yeah, the first one, the centimeters per second, would be your change of velocity in a given time seconds. And that's what we were doing in the lab today. So 30 centimeters per second squared. Okay. But most of the time in real life, it's miles per hour per second, kilometers per hour per second. Sometimes maybe miles per hour per minute, like the launch of a satellite, of a rocket, that's going pretty slow, so you might do its average acceleration in miles per hour per second, per minute to begin with. But then after a while, it's really accelerated. So, yeah. Okay. So, again, here's some graphs. So get used to sort of seeing these. Notice always what your units are. Here it's speed in kilometers per hour, time in seconds. If you're going on at a constant speed, what does that tell you? Zero acceleration, absolutely. No change of speed over time. That's a zero acceleration. You're on cruise control, okay? You're not changing speed at all. This one, however, if there's your speed, there's your time, and you're increasing the speed, that would be a constant acceleration because that's a straight line. Now, if that had a curve to it, it's not. If it's constant acceleration, what do we call that? Another term for it? Say again? Uniform acceleration. Anytime you have constant straight line acceleration, that's uniform acceleration. Then you can use this second definition for average velocity. In today's lab, we'll be doing that. All right. So I think I've hit all the formulas here. The book does use the deltas occasionally, but most of the time with distance and velocity, very seldom they use it with time. Really, it works with time too, but they just don't use it. So let me clear this out of the way, and let's do example 2.3. A bicycle moves from rest. What does that mean? What zero? Okay, so what would be zero? Okay, that's not minutes. Meters per second. What does that measure? Velocity. If it's at rest, it has a zero velocity. Not moving. It may not be at a zero position. You may be at mile marker 514, That's not a zero position necessarily, but if you're sitting there at the mile marker, your velocity is zero if you're sitting still. So it's from rest. That means, from rest means V initial is equal to 0. That's what that means. Okay? 2, not the number 2, but 2, 5 meters per second. Okay, and if it's M by itself, that means meters. What does that measure? What would that be? Which velocity? Final, that would be the final. If it's moving from that to that, this is your final velocity of 5 meters per second. Okay? In 5 seconds. What would that be? This would be your delta t or your t. The book just calls it t. Okay? What is the acceleration? So what are we looking for? A. That's your unknown. And what's the formula for A, especially if it relates to velocities and time? Okay, delta t over delta v. What's that? I think so, because this would be in seconds per meters per second. That would be second squares per meter. Yeah, that was backward. Your units will let you know that. Okay? So, all right. Yes, that will be delta V over delta T. If you want to put the arrow, you can. That's up to you. I do it just to remind myself those are vector quantities. So this will be V final minus V initial. And since they didn't give us initial and final time, all they did was the delta V. That would just be over 5 seconds. Okay? I mean, delta T. And what was your V final minus V initial? 5 meters per second over 5 seconds. Oh yeah, minus 0 meters per second. And that would be 5 meters per second over second. I'm sorry, over 5 seconds. The 5's cancel out. That would be what acceleration? 1 meter per second squared. Very good. Or 1 meter per second would be fine too. Both of those are legitimate answers. Okay? What's that? No, because both of them are in denominators. Say again? Yeah, you're dividing by this and dividing by it again. If this were a per second down here, per second would cancel out. But per second here and per another second there, that's 2 of them in the denominator. Here's the other way to think of that. Good point. 5 meters per second divided by 5 seconds, right? Is it that what that long division line means? Divided by? So that would be 5 meters per second times 1 over 5 seconds. Okay? So what's in the numerator? Well, your 5's go out, and you would have 1. And what's in the numerator is meter, and what's in the denominator is 2 seconds, so that would be second squared. So if writing them vertically gets a little confusing, write them horizontally. Usually the units make a little more sense that way. So that's a good question, good point. 1 meter per second squared. Okay with that? All right, let's do example 2.4. An automobile uniformly accelerates from rest. What does that mean? Okay, but what does that mean in terms of our parameters? Initial velocity is 0. Rest, the velocity is 0. Okay? At 5 meters per second squared, I guarantee you it can't do that for very long, but it can do it for a little bit, for 6 seconds. Okay? What is this a measure of? Meters per second squared. What's used? That's an acceleration. You're absolutely right. What is 6 seconds? That's your time. Okay? What is the final velocity in meters per second? What are we looking for? V final, there's your unknown. And you're looking for it in meters per second. Well, let's see, you got meters, second. Yeah, everything's good, so it should be fine. Now, let's write the only formula that we know so far that relates those 4 quantities together. What formula would that be? Acceleration equal V final minus V initial over time. Very good. But since we're looking for this one, that's your unknown here, let's rearrange it. Now we're going to do it literally. You could put the numbers in and didn't do it, but let's just do it literally. First thing we're going to do is clear that denominator. Multiply by time. Okay? So that gives you V final minus V initial is equal to AT. Now you add the final velocity, because you're looking for this one. Add your initial velocity to both sides. And usually we write it this way, but it doesn't really matter. V final is equal to V initial plus AT. Okay? Now we can just plug and chug. Okay? And what do we get? What's your... Otherwise, you chug and plug. So you just decide. Okay? What's your V initial? 0. That was easy. I could have done that one. 5 meters per second squared times 6 seconds. That's your time. Now this second cancels one of the seconds out. It's second times second, remember, so it cancels one of them out. So this gives you 5 times 6 is 30 meters per second. That's your final velocity. Now,
Why you canceling units out with multiply?
what?
Why you canceling units with multiply?
If you set it up, 6 seconds over 1.
Yeah, I keep forgetting that meters every second is actually. You're good. I got it.
Okay. And that helps know what the unit is. Now, 30 meters per second, folks, that is moving. Because remember the last one, 72 kilometers per hour, which is around 60 miles per hour or so. That would have been, that was 20 meters per second. 30 meters per second, that would be about 90 miles per hour. About, I'm just roughly guessing. Okay, that's moving. So that's why I said, you're not going to accelerate for that for very long. That's a huge acceleration. Maybe you can do it for 5 seconds. My vehicle, I don't think it can. Or 6 seconds. Mine would be grinding like crazy by the time. Slow down over here. What's that? Yeah. Okay. Do these make sense? Okay. So the answer was 30 meters per second, which is going pretty fast. That's again about a third of a football field in a second. I don't think I can do that. I know I can't do that. I know I never could do that. All right. Now, before we move to forces, there is a blurb at the top of page 31 on Science and Society, Transportation and the Environment. Sounds like a pretty interesting blurb, well worth a read. If there's something in there that you think, hey, I'd like to do a paper on this, definitely something worth looking at, okay? Now the next page, before we get to forces, here's another example, example 2.5. So let me back up one more and clear this one more time and do example 2.5. An automobile moving at 25.0 meters per second. 25.0 meters per second. What's that represent? A velocity. And what velocity you reckon that might be? Initial, because that's what it's starting with, okay? Comes to a stop. What does that indicate? Final velocity would be what? 0 meters per second. So this time they've got them reversed. You're not starting from rest and speeding up. You're starting from a velocity and coming to a stop. Okay? And it says it does this in 10.0 seconds. What's that a measure of? That's your time or time interval, delta t or t. Very good. When the driver slams on the brakes, is it going to take him 10 seconds to come to a complete stop? Huh?
Depends on how much weight you got.
Depends on what?
How much weight he's got behind you.
Could be. Actually, that could speed you up or slow you down.
Well, if you're an 18-wheeler, it's going to slow you down. It's gonna take
Yeah, exactly. That is a good point. So that's why 18-wheelers probably shouldn't be going around at 25 meters per second, because that's probably around 70, 75 miles an hour, and maybe 70. But boy, it's going to take them a while to stop. Okay, that's why you don't tailgate. Okay. What's that?
That's why I got air brake.
Okay. All right. When the driver slams on brake, how far does his car, this is an 18-wheeler, his car travel while stopping? So you're looking for what? How far? Distance. That's your unknown here. Now, we haven't done one with that, have we? Okay? We sort of have. What we're going to have to assume here, slamming on brakes, we're going to assume that's a uniform acceleration. Of course, it's a negative acceleration, but uniform. That it's going to slow down at a constant rate. And if you do that, what does this tell you? Say again?
Nothing.
Yes, it does. If you've got a uniform acceleration, which we'll assume, slamming on brakes, go. Okay, it's going to be a negative acceleration for sure. Okay? But we're going to assume that is if you have a uniform acceleration, what does that mean? Read the second bullet. Average velocity simply related to initial and final velocities. How is it related? Averaged. Initial plus final. How do you do an average? Divided by 2. If you got two things, and that's what we got here. So what would be his average velocity then? V bar would be what? 25 plus 0 divided by 2 would be 12.5. Is that what you said? Okay, I thought you did. Okay. 12.5 meter per second. Okay, anytime. Okay? All right. Can we now find out the distance? What's the formula there? Exactly. Multiply this by your time, 10.0 seconds, and that will give you a distance, right? Because your seconds cancel out, so units are your friends, and what would that be? 125 meters. What's that, folks? That's further from end zone to end zone, because those are about 10 more yards, right? So that would be 120 yards, 125 meters beyond that. A full football field plus some. That's how far it takes to stop at 25 meters per second, which is around 70, 75 miles an hour, I think. I haven't done it in my head. I mean, I'm just guessing. Huh? Well, it could be. If the road's wet, like today. On a wet road, no. Huh? No, on a wet road. Yeah, and if you're on slick grass, it could get easily. Okay. Okay. What we might call some of this is wishful thinking too, but yeah, it's what's that? Yeah, well, okay. Let me give you a situation. Before I started working here, that year in between when I was at Southern Research and started working here, I was teaching part-time at Jeff State. I got up one morning and was actually right on schedule, a little ahead. I usually wouldn't take the interstate if it looked like the morning rush was really slow. And I drove down the road that I could see it. Looked like it was moving really well. I said, well, that'll miss a lot of lights. I'll get on the interstate. So I did. But it had just started raining that morning. Just a drizzle. Okay, and say again? Yes, exactly. And I contend to you, it was going to be a long time before it was going to stop, no matter what, whether you had ABS or not, because the oil right on top of the water, like I said, they were really moving, and I had to really speed up to get onto the interstate. We crested a hill, and all I could see were brake lights in front of me. Two cars ahead veered to the left and squeezed in the last place there. The car ahead of me veered to the right and squeezed in the last place there. There was no place else to squeeze. I hit the brakes and it didn't do a thing.
You stop the brakes?
Huh?
You stop the brakes.
I didn't stop. I just hit them, but it didn't matter. Actually, what happened, it hydroplaned. Nothing was going to stop that car. And I got as far over as I could, but still caught his back left, right on my front left.
Yeah,
And,
no downforce.
huh?
You have no downforce.
Well, the thing is, when you have oil on water, it doesn't matter what you got.
That's a friction issue.
Yeah, that's a friction issue, exactly. Okay, that's what I said. That's what I said. It depends on your surface, okay?
Yeah, because other than NASCAR, I never did go to the pits because they're going too fast.
Okay. All right. Okay. We have one more, by the way, one more example, 2.6 here. What was the deceleration of the automobile in example 2.5? That was the easy one. What was the acceleration in this problem we just did? What's your acceleration? What formula is that? It's been a while, I know, at least 30 minutes, okay? Change of velocity over change of time, right. What was your change of velocity? Yes, it's V final, which is 0 minus 25 divided by 10.0. And that was a 25.0. Yeah, 25.0, you're right. What would this be? Yes, yeah, this is meters per second, and this is seconds. Y'all are learning, huh? Okay. And what you got? Negative. And 2.5. Move the decimal. 2.5 meters per second squared. That was the deceleration. Oh, one more zero there because we have three significant digits. Negative 2.50 meters per second squared. Good deal. Make sense? Now, I have heard that some folks did this. It might be doable here, but it would take a bit of effort and probably too much time. But doing some acceleration patterns. And actually they're going to combine what we're doing next with it too. It's a pretty nifty experiment. Yeah, they're talking about leaking radiator. I'll give you something that you don't have to have a damaged product to do. Okay?
I got some.
Okay, you got one that's leaking? Okay, good. No. But what you could do is if you had, I would say, either one or two people in the car and completely in neutral, brakes off and everything else, and you got maybe three guys behind pushing on the back, okay? Good thing to have scales between you and the car. That measures the force in pounds that you're pushing, okay? And once you get the car rolling, if you can keep the force pretty equal, maybe shoot for 25 pounds each, 50 pounds each, whatever you can go for, do that. Then if three people are doing that, that could be 75 pounds or 150 pounds of force, okay? And the person in the car, every second, is putting out a marker, like a little traffic cone or something, there with the door open. And then at the end, you measure your distance, you measure, and you see your actually velocity is increasing, you're accelerating, you can calculate that, relate that to forces. It really is a pretty good thing. The trouble is nice to have a nice flat parking lot. And most of ours are not always that flat and sometimes not all that smooth either. So it would be sort of a pain to do here. And you would also have to make sure nobody else is going to be driving in, and So it would be a little hazardous, but if we get it all blocked off, that could be done. That's the acceleration pattern they were talking about. They're saying if you had a leak in your thing, but I think it's better to use traffic cones to measure your distance, okay, or how far you go between a certain time period. All right, now we're ready for forces, okay? All right, let's go a little bit on the historical background. Yeah, I'm just kidding. All right, originally, good old Aristotle, we've heard of him before, right? He never really mentioned forces very much that I can recall. He assumed that heavier objects fall faster than lighter objects. Would you agree with Aristotle or not? All right. We'll see. Okay? He also said that objects moving horizontally require continuously applied force to maintain their velocity. Would you agree with Aristotle or not? All right. Uh-huh.
You have another cannonball at the same height, and you dropped it at the same time you shot the cannonball. Which one was the ground first?
One drop straight out.
Both of them hit the same time.
They definitely will. We're going to get to that a little bit later. Yeah, we will get to that a little bit later.
You know, maybe cannonballs that start the same height.
Yeah. Yeah, they start at the same height.
It's still falling. It's just
Yeah.
going a different direction.
You're right on the money there, and we'll do one almost just like that. Only it won't be cannonballs; it'll be arrows. But
How about bullets? That work the same?
it would do the same too. It's just that you got a lot further distance that you have to track that and find out where it lands, and that would be tough. Arrows go a little bit slower, and you can do that all in one field. You know, bullets. They just, huh? No, we're not going to shoot. No. Dream on. Okay. All right. But objects moving horizontally require, this is what Aristotle thought. Okay? He relied on thinking alone. He observed, but he just thought about it. So you agree with him that heavier objects fall faster than lighter objects, right?
Yeah.
Oh, some of you do. Okay, some of you don't. So that means two objects with the same weight should fall at the same rate. Is that what you're saying? Oh, well now you're getting into something else. These are all old anyway. Here are two pieces of paper. Would you say that these two pieces of paper should fall at about the same rate? Oh, well let's see. He's already, oh yeah, they're pretty close to the same rate. Now by adding mass to it. Nope, same mass. So they should fall at the same rate, right? According to Aristotle, right? Okay, same mass, same weight, but they fell at different rates. Okay? So obviously there's something else involved with this. It's not just how heavy the object is. Okay, yes, resistance. And that's the same thing here too. You have to continually apply force if there's a resistance, okay? Which most of the time there is. But if you eliminate the resistance, no, you don't have to.
So would that Aristotle thinking would be true of a vacuum, right?
Yes, it would be. No, yeah, except, no. He said that heavier objects would fall faster. Now, actually, on one of the moon landings, they did this. They really did. The astronaut took a hammer and a feather on the surface of the moon. Now, what's true about the surface of the moon? There's what?
A lot less gravity.
There's less gravity, but there's still gravity. But what else is true there? The what? Craters, yeah, but he's on the level part. He's not on the edge of a crater.
No wind.
no wind, but not just no wind, no air at all. He drops the hammer and the feather, and guess what? They land at the same time. Because it all depends on the resistance. It's not the object, it's not the weight of the object, it's the air resistance. It kept the ball, the flat paper held it up where the ball fell faster. Okay?
So if you took that piece of paper
Uh,
and you had a block of wood that was the same size of that paper, it's going to cause the same amount of wind resistance, they still get the same time.
okay, but they have, okay, not quite, okay? Well, assuming the block of wood was heavier than paper, which is a good assumption, right? Okay. And here's why. Well, we'll get to it later. But the thing is, the weight does matter, and that's why you think the heavier objects fall faster. But the deal is something called the terminal velocity. The terminal velocity is where, and this is getting ahead of where we are now, so it may not make sense to you now. What makes an object fall is force due to gravity, is pulling it down. Okay. Now what impedes that, as in that piece of paper, was the air resistance. Okay. Air resistance depends on the shape of the object and also the weight of the object. So a heavier object will have a larger terminal velocity than a lighter object when they have exactly the same shape. That's what he was seeing. He was looking at terminal velocities, not, and that depends on resistance. If there's no resistance, they fall at the same rate because there's no change in terminal velocity. There is no terminal velocity. It just accelerates the whole time through. But that's why when the guys or gals jump out of an airplane, they're going along at, they will reach a terminal velocity at some point, and that may vary. If they're doing like this, it'll still be fast, but not as fast. They do like this, it's going to be really fast. They become bullets going down, okay? But then if they pull the ripcord, then all of a sudden they slow down because your terminal velocity with all that air resistance is going to be much, much slower. So they are yanked. They feel like they're being yanked upward. They're still coming down, but this is a much smaller rate because the terminal velocity with this is much less than the terminal velocity of that, which is less than the terminal velocity of that. Okay. So you see the same weight, if you change the aspect of the fall, yeah, it can change your terminal velocity. So he was looking at terminal velocities, but that wasn't what he was saying. He was saying heavier objects fall at faster. So your question about in a vacuum, the moon was basically a vacuum. Okay? So they fall at the same rate. And the same thing would be here too if there was no either friction horizontally or air resistance against that, you don't have to constantly apply force. It's only because there is resistance. But y'all are jumping way ahead, but this was Aristotle. Along came Galileo first, and then later Newton. Galileo did the earlier experiments. By the way, all three of these are potential paper topics, as with many other things we talked about. So Galileo actually did, now, he was so far back there, they didn't have good ways to measure time. Okay, they didn't have stopwatches and stuff. Things like sand through an hourglass or drips of water or something. I mean, not very good ways, but using the best time measurement that he could, if he just dropped something, that was going to fall too fast. So what he used was inclined planes, which is what we're going to use in lab today. Okay? And he did it both letting the balls roll down the plane or also rolling the balls and letting them go up the plane and stop. So he did a variety of experiments like this, but this is the key, folks. He found out, and Newton followed up with him, all objects fall at the same rate as long as you take resistance into account or eliminate the resistance, either one. No force is required for uniform horizontal motion as long as there's no resistive forces, okay? They did their reasoning based on measurements of controlled experiments. And by using balls rolling on a plane, he eliminated a lot of the horizontal resistance, because the rolling friction is very much less than sliding friction or something like that. But the other thing is in the vertical motion he did. Now, actually, one of the first demonstrations I used to do when I was teaching, back when we were Western State Technical College, which wasn't before you were born, but it was a long time. You were very small back when we were at that. We didn't have a lab with the physics classes, so all I could do was demonstrations. We didn't have time for labs, and I actually did this one. This building has 3 stories on that part of the building. There are only 2 stories here, but on that part there's 3 stories. And there was a stairwell behind what used to be the physics lab back there. Now it's used mostly for biology classrooms and sometimes other large classes like speech and stuff. But there was a door back there that was always kept locked, but there was a stairwell in it. So I got security to unlock it for me. I went up to the very top flight, and there was a window there. And I had the students be down on the ground, the grassy part down here, and I had a 1,000-gram weight and a 1-gram weight. That's a difference of 1,000 times the weight. Okay? Actually, I said gram. Grams measures mass. So that'd be 1,000. Close to 10,000 newtons as opposed to 10 newtons. Okay? Not exactly, pretty close. Okay? So obviously one object 1,000 times heavier than the other. And they were just weights. Now I dropped them from 3 stories. Which hit the ground first? Same time. Because the shape was so the resistance wasn't much. They were similar, and basically they weren't going fast enough to even come close to reaching terminal velocity. So, yeah, they fell at the same rate. Okay, even though one was 1,000 times heavier than the other, and they fell at the same rate. Actually, the first time I did it, it didn't work too well. I didn't realize someone had strung a fishing line or something like that. I didn't see it along there, and one of them, the hook on it, caught on the fishing line. Do you think I could have done that if I tried to do it? And one spun around the line, the other one hit the ground. I had to do it again, but they did fall at the same rate. Couldn't believe it. All right. So, what's involved here? Forces. Forces are things you applied, and by the way, and this I can remember, when I was a freshman in high school, we had an old football coach who was as mean as a snake. Okay, everybody was in fear of him. His name was Cooley Hubert. Okay, he was on one end or the other of the longest pass thrown in Rose Bowl history. When Alabama played one of the California teams in the Rose Bowl sometime decades ago, probably close to a century ago now. I mean, he was old at the time I was a freshman in high school, so it would have been close to, a long time ago. And I can remember him saying, a force is a push or a pull. He sounded just like Bear Bryant, by the way. He was there before Bear Bryant, but he sounded just like him. A push or a pull. Now that's one definition of it, and it's not a bad one, because that's a pretty good description of what a force is. A push or a pull, capable of changing an object's state of motion. What would you say the state of motion of that desk was? Say again? Okay, yeah, it's zero velocity, right? No motion. Now, I'm going to push on it. Oh, I did move it. Quite often they wax the floors here and wax it to the floor. And I can push to when cows come home. There I'm pushing. Okay? I am pushing. You can see my fingers. I'm not capable of producing motion. Actually, I am exerting a force on it, but it's not creating any motion. But if I push hard enough, then I do get some motion. So a push or a pull, I exerted a force on the desk. Okay? Capable of changing the object's state of motion. The overall effect is determined by the vector sum of all the forces. And we call that the net force. I'll give you another dumb example here. When we first moved into the house where we currently live, my wife really liked the house. It was an old Tudor-style house, built in 1930. Thank goodness she likes old things, so she married me. We won't go there. Okay, so anyway, they had lots of trees in the yard. Now, I like trees. She liked trees. The first house we lived in Birmingham, there was a tree on the house next to us that way, and one that next to us this way. We had no trees until we planted some, but it was a very small yard, so we didn't plant very many. But anyway, this had lots of trees. In fact, we really had too many trees. There were a couple of really ugly, scraggly, crooked pines that were trying to grow up underneath pecans and oaks, and they were crooked trying to get to the sun, So they were really lousy looking trees. We didn't know why they had left them there, but they did. So her dad and brother-in-law came down from Huntsville, and we were going to cut those two pines. But we were trying not to damage the other trees, okay? So we took a rope, and they were so crooked, we had no idea which way they were going to fall. So we took a rope and threw it as high up as it could to catch some limbs up there. And so it came down on either side, and Dan took one, he's my brother-in-law, and I took the other. Now, the maximum force we could have exerted if we both pulled together while Mr. Brazil, her dad, cut it with the chainsaw. So if we had pulled together like this, we could have exerted the maximum force on the tree. Would that have been a good idea? Why not? The tree's going to fall right on top of us. So we elected to pull at an angle like this. Now that cut down on our net force on the tree, because you see it's a vector sum. When we pulled like that, he was pulling this way, I was pulling that way. This was the force he was pulling, that was the force I was pulling. You can break that into two components. There was a component this way and a component this way. A component this way and a component that way. These two basically canceled each other out. So we were pulling, in a sense, sort of against each other in that respect, but the net force would then be in that direction. The sum of those two forces that were in the same direction. These are in opposite direction. The net force was, they were canceled out. So even though we got less force, it was still preferable to have the tree fall between us rather than fall on us. Okay, so dumb example, but that's absolutely true. If you've ever paid attention to power poles when you're going down the road, we have a place up on Smith Lake, and boy, the roads around there in between Arley and Houston, they just do all sorts of things, and the power lines are just one side, then the other side, trying to keep up with the road, but go the shortest distance you can and stay on either side of the road. But every time there's a bend in the road, what do they have to have for the power lines? A guy wire. Why? Yes, the force would be pulling the poles this way, and soon those poles are going to snap. So they have guy wires, and you can look at them. The net force they're trying to put on that pole is zero. The guy wires are pulling this way, the power lines are pulling this way. So you see that all the time, net forces. Here's a dumb example here. Here's a ship. Looks a lot like an ammunition ship, but it could be any kind of cargo ship. Okay? I was on an ammunition ship in the Navy. And if you have two tugs pushing on the side of this ship, and they're both pushing with 1,000 units each, then what would be the net force on the ship? 2,000 units to the east. However, if they get their signals crossed up, and they can't see one's pushing on this side with 1,000, one pushing on that side, not knowing the other one's over there, are they changing the motion of the ship any? No, because now the net force is zero. They're both pushing with 1,000 units each, okay? But the net force is zero because it's a vector addition, not a scalar addition, okay? But if the one over here is a small tug, only pushing with 1,000 units to the east, But the bigger tug is pushing with 2,000 to the west. This one on this side saying, what is going on here, folks? I'm pushing this way, but the net force is that way. The ship is pushing me backwards because the other one's pushing there. The net force would be 100,000 units to the west. Make sense? Vector addition, not just scalar addition. You don't just add 1,000 to 1,000 and have 2,000. You don't. You have to include the direction in it. Okay? So, let's look at what they call the fundamental forces. Okay? Fundamental forces. Okay? The most basic of all the interactions we have in nature made up of these basic fundamental forces. The first of these is gravitational force. And we experience that all the time. We're experiencing right now. I'm standing here, the earth is pulling down on me, and the floor is pushing up on me. We'll get into that later. But always experiencing gravitational force. Okay? Even those astronauts up there on the space station, not much gravitational force, but they're experiencing a little bit. Okay? These are mass interactions. This accounts for the motion of planets, stars, galaxies. All these things are moving because of gravitational forces. Okay? Now, I was thinking of saying this earlier, but I declined. I guess I'll go and say it now. Remember Aristotle's thing, heavier objects fall faster than lighter objects? Okay? Aristotle knew he wasn't absolutely correct like this. He had to split objects into two types. He said you have terrestrial objects, in other words, objects on the surface of the earth, and then you have celestial objects, those up in space. He said different rules apply depending on whether it's terrestrial or celestial. Galileo and Newton said, no, it's the same forces, same everything. It's just whether you have friction, resistance on Earth, and none in space. You don't have any thing. So, moon going around the Earth, okay? You couldn't do it if there was an atmosphere there. You know, you couldn't do it within our atmosphere. That's what a falling star is. Something trying to fall through the atmosphere, it burns up, okay? Because the atmosphere slows it down, friction. But the moon keeps going around, the planets keep going around the sun. Some are massive planets, some are small. Yeah, doesn't matter. Aristotle's doesn't apply. But he had to split into two classifications, okay? So, gravitational forces, mass interactions. And that's why it said motion of planets, stars, galaxies, all these go by gravitational motion. Now, the second of these is electromagnetic forces. And you probably experienced these before too, or you've seen them in action. Have you ever done the thing, I can't do it anymore because I don't know. Combing your hair, okay? Combing your hair with say, acrylic comb or something like that, and then picking up little pieces of paper with it. Have you seen that demonstrated before? What you've done is rub electrons off your hair onto the comb, making it negatively charged. Little pieces of paper are neutrally charged. Those unlike charges, you can actually lift the paper off the table. You have to do it. If you have non-oily hair, your hair has to be pretty clean, and you also have to be non-humid days. Today it probably wouldn't work very well, but you can do that and try it. That's electromagnetic. Which would you think is a stronger force, gravity or electromagnetic forces? Say again?
Electromagnetic.
You're right. Okay? The difference, though, gravity will act for a lot longer distance than electromagnetic will. Because, like I said, the comb will pick up the paper only if you get close enough. And you do, it'll pick it up. So it overcomes the gravitational force only for short distances. Up here, doesn't even feel it. Okay, so, yeah, it's a stronger force. And here, these were mass interactions. These are charge interactions. Remember, negative charge on the comb, neutral on the paper. If that's negative and positive, it's even stronger. Okay? Electricity and magnetism both act that way, except for electricity, it's charges. For magnetism, it's polarity. Okay, so same type thing. Have you ever been in Mobile and watched some of the cargo ships being loaded or unloaded? What did they use?
Magnetic crane.
Yes, they use electromagnets to pick up the metal thing, drop it, turn off the thing. Yeah. They used to do it by tying it down. Then, something isn't quite balanced and you can have things falling. Yeah, really bad. That electromagnet picks it up, drops it, picks it up, drops it. Much stronger than gravitation. Okay? This also pertains to atoms. Well, that's what it's doing when you comb your hair. Atoms and molecules, you change the electron configuration just by one electron, you can change all sorts of things. That's how you make molecules. That's what chemistry is basically based on. And in a few chapters we'll get there. Now, this doesn't sound very specific, does it? Weak force, okay? They say a weak force, but it's not really all that weak. It's stronger than either of these two, but again, at much, much shorter distances. These are the forces involved with certain nuclear reactions, okay? That's not very specific either. When you get your book, take the time to read it. It still doesn't go into great detail, but it'll have a sentence or two more than what it have here. But then you have other nuclear forces that call strong nuclear forces. Now, do you think these are stronger than electromagnetic or not? Definitely. And here's why. What are nuclei made of? Nucleus of an atom. Second. Protons and neutrons. The electrons are flying around out here. So within the nucleus, it's only protons and neutrons. Now, what are the charges on protons? Positive. What are the charges on neutrons? Neutral, no charge. So wait a minute. How do you have these big old, relatively, protons with these positive charges fitting together so tightly? I mean, incredibly tightly. Why aren't they pushing apart? Because positive, like charges should be repelling like crazy. In electromagnetic, they do repel like crazy. Have you ever tried to, now this is with magnets, not fake, but take a north pole of a magnet and hold it against the north pole of another magnet? It depends on the strength of the magnet, you just can't do it. It will not let you do that, okay? Really weak magnets you might be able to. So what in the world is holding those protons in that tiny little space? Why aren't they flying apart? These strong forces. Much, much stronger than electromagnetic forces. Now I can't tell you, even if I had a real good understanding of it, how these work, because the equations and the things that are going on there way beyond the scope of this book, way beyond the scope of what I understand. It's quantum mechanics, okay? So those strong forces are some of the strongest in the world, but their distances extraordinarily short, so they only exert that for a very short distance. You really don't need to know too much about that, except that's just sort of general background information. So let's first start with horizontal motion on land. Okay? They're splitting motion into three classifications. Remember back one of the slides we did last time, we're going to look at horizontal motion, vertical motion, and then compound motion, which is a combination of the two. So we'll do horizontal motion on land. Okay? Let's roll a ball down the floor. Okay? Now, once it leaves my hand, which I'm exerting a force with my hand, once it leaves my hand, what are the forces acting on the ball? Okay, gravity is pulling down on the ball, but the floor is pushing up on the ball, and those basically cancel each other out. Okay, net force is zero. But you hit it. Rolls along the floor, and guess what? If you can hear it rolling, that means there's friction. Okay? Because if there were no friction, There wouldn't be any vibrations coming off of that for you to hear. So yeah, if you can hear it rolling, yeah, that's why it stops, because there's enough friction. Now, it's not just between the wheels and the floor, it's also the wheel and its axle. I mean, there's lots of friction in that, okay? So there is some friction with the floor. But even if the floor was absolutely slick, no friction there, there's still air resistance, okay? So you also have a resistive force of air. So if you have no applied force anymore, now actually the way this is drawn, I would be rolling it from this direction. Once it left my hand, I have no more force in that direction, but the air resistance and the floor resistance are this way, so the net force is against me, so that ball will ultimately slow down and stop if we had a long enough room, okay? And it was going slow. Now, if, however, I was able to keep applying a force, then, like, blowing on or something like that, exactly counterbalancing that, then it would go on. If the net force is 0, it does not slow down. It just keeps rolling. Do y'all like the Winter Olympics? I don't mean the figure skaters. I don't mean that. Yeah, I like them too. Okay, but how about that curling? Have you ever seen them do that? It's the strangest to call that a sport. Yes, exactly. They're sweeping everything in front of, trying to reduce the resistance as much as possible. It actually is a stone. It's a very well polished stone that they're sliding across the ice, and the people are going along sweeping, trying to keep it. And then when they want it to slow down, they quit sweeping, hoping that it'll hit some resistance there. They're aiming it toward the other eye. It's a strange sport. But what they're doing was trying to adjust this air resistance. I mean, the floor resistance. Surface resistance, we'll call it.
Basically, it's sport where you roll a stone and sleep.
It's not rolling, it's sliding on the ice, yeah.
Slide the stone and clean it in front of it.
Yeah.
It's kind of like shuffleboard, but you got clean where it's going.
Yeah. Yeah. All right. Okay. So here's what we're dealing with here. Natural motion question that Aristotle brought up. Is a continuous force needed to keep an object moving? No, if there's no unbalanced retarding forces like friction of the floor, air resistance. If there's none of that, no, you don't need it. The continuous force is not needed. But if there are unbalanced forces, and this is where Aristotle sort of had it right. On the surface of the earth, there's always friction. So that's why I said terrestrial, these rules work. Celestial, they don't. But he still had it not quite right. Now, what are we dealing with here? This should almost be another subject, but it really fits here too. What do we mean by inertia? Where do you ever hear that word? Huh?
I don't remember what it means. I've heard it.
What's that?
I've heard it, I don't remember.
Okay. What's the first 5 letters there? And what does that mean to you? Anything?
Same as inertia.
Okay. It basically, inert usually means nothing happening. I can imagine my wife saying, sometimes you're just inert, aren't you? I'm not inert, but inert. No. It's just doing nothing. Just sitting there. Couch potato, okay? Inert, okay? And that's part of inertia. This object, this desk, is sitting here because there's no net forces acting on it. Now, to make it move, you're going to have to do something to it. And to make it move is a little less difficult than making that move. Why? There's more inertia in that than there is in this. If there's a ping pong ball, very little. In fact, the setting it down, the wind may actually make it roll, okay? So inertia is a measure of an object's tendency to resist changes in the motion. Now, we think of it being initially at rest, but it doesn't have to be, okay? it could be initially moving, and inertia still is a tendency to resist any changes in that motion. That desk is at rest, this is at rest, but say we had a bowling ball rolling down the floor at us. The inertia is the tendency, the measure of the object's tendency to resist changes to motion. I don't think I want to put my foot out there and stop the bowling ball. Okay? I might do it, but I'd like to have a steel-toe shoe if I'm going to, okay? Because it's probably going to hurt if it's going pretty fast, okay? So inertia, we think of it in the inert state, meaning at rest, but it could even be motion. Inertia is the measure of an object's tendency to resist the changes in the motion. I think that the catchers who used to catch for Nolan Ryan, and who was the guy for the the Diamondbacks, Randy Johnson, some of those, and Bob Feller from way back, really threw the ball hard. Those catchers, I have a feeling they understood inertia because they were having to change the motion of those fastballs coming in, trying to stop them. Today, I'm sure there's fastball pitchers. I don't know as many of the names, okay? Whereas those who are catching slow pitch softball, not nearly as much pain probably involved, okay? So let's look at this concept of balanced or unbalanced forces. We saw it mentioned here, no, in the absence of unbalanced retarding forces. So what do we mean by that? Motion continued unchanged if there are no unbalanced forces. That's almost double negative here. Without unbalanced forces. If you don't have any unbalanced forces, motion continues without change. Okay? So let's say we have a satellite out there in outer space, no gravity, no air resistance, nothing, natural motion in free space is constant velocity. Never changing. And actually we do have a couple of spacecraft that were sent out decades ago that have already left our solar system and are going, and they're not going to be able to send back data for long because they don't have a power source. They were getting light from the sun. They're getting away from that, but they were still collecting data as they went, past the solar system until they couldn't send it anymore because the batteries died. That's natural motion in free space. Okay? Constant velocity. Retarding forces are unbalanced forces, they decrease speed. So if you had, let's see, I think they'll show a picture of it. If there was a retro rocket here that you fired, that's moving in this direction, but you fired it so its exhaust is going here, that's going to slow down the motion of that astronaut. You have to have a retarding force to slow it down. But if you put the rocket on this end and fire it this way, then that would actually increase the boost of speed if the rocket was pushing in that way, in other words, firing in that direction. Okay? What if you had a sideways force? What would that do? That's changing its direction, which is still an acceleration. All three of those situations were acceleration. Negative acceleration, positive acceleration, change of direction, acceleration. All three were accelerations. Okay. Now, let's go back to the sun. Big old mass, huge mass, the sun. It's pulling all of the planets and comets and everything else toward its center. But we have a velocity, initial velocities like this, so the combination of our motion this way with the gravitational this way, that's what keeps us orbiting around the sun. That's what keeps the moon orbiting around the earth. Okay? Because you have a combination of those, a sideways force, the pull of the earth, of the sun on the earth, and that changes the direction, so you do have circular motion. It's actually elliptical motion around the sun. Okay. I think we're going to have to stop there because we're right at, in fact, we went a little over 3:45. There is one more thing I wanted to point out to you here. Mistakes and misunderstanding. Some of these are sort of fun, and some of them are a little innocuous. But I remember I did have friends who were in a math class, and the guy asked them this question: walk in the rain or run in the rain, which are you going to get wetter? Say again? Okay.
You just get wetter faster.
Okay.
It's gonna be the same amount of weight.
It's the
It's
same,
gonna be
but
so
you have
hot.
running, you have more rain in front of you.
Okay. Okay. The distribution of rain will be different. Okay.
Yeah, but you'll be running into more of it.
So the front will get wetter and the back will get, yeah, okay.
Some of that gets-
But the real key here is how long are you out there?
The same
So,
amount of time.
yeah, if you're the same amount of time, you're going to get the same amount of wetness. It just may be distributed differently. But if running in the rain gets you out of the rain sooner, you actually are less wet then. So, to me, what's the point? Okay, yeah, but it is a fun question to look at. We'll start next time with falling objects. Okay. Okay. What we're going to do now is have a little bit of a break time. The reason for this, several fold. Number one, I've got to shut down this for now. I'm not going to shut down the screencast-o-matic, but I'm going to put it on pause. But number two, we're going to transition to the lab, and it's going to take me just a short time to set up the lab. I didn't have time at lunch today because I had about a dozen other things I was trying to get done. So it's going to take a little time. Are any of you here need a copy of the first lab? Okay. Let me get that to you first. And what I would recommend you get with someone who was there for the first lab and get as much information as you can from your partners.
Are we going back in here?
We'll probably go to the same room we went to before. I saw some other hands go up. Were there any others?
What the lab's due?
What's that?
What the lab's due?
1 week from the time we finish it. But you can turn it in at the time you finish if you want to, but if you need some more time to look over it, you can do it. So it'll be at least 5 minutes before I get down there, so take a little bit of time for a break. Questions left over from the last lab. I know we didn't quite get to finish. Oh, before that, let me mark the roll again because I have to mark the roll twice. Sort of silly rules, but they're the ones we're having to live by. Okay. Wrong class. Okay. Right class. James, I know you're in here, but right there. Okay, gotcha. Okay. Parents, I see all you. Camp, yeah. That, okay, with the hat on. Okay. Swim is there working. And Dart is there. Okay. Mason is right there in front of me. Okay. Samuel's right there. Ryan is right here. Alfred is right there. Jeremy is right there. Gotcha. Charles is there. And Brittany hasn't made it in yet today. Trevor is there. And Terry hasn't made it in yet today. Okay. Got everybody we started with. Too bad no one else showed. So, let's get to the first lab. I want to know if you had any questions on this before we move on to the new lab. Okay? Now, for those who weren't here, please read the labs. They pretty much are self-explanatory, but you almost have to have the equipment to do them. So to get your measurements, you're going to have to get with someone who was in the lab or come arrange a time with me and we'll go through the things as much as we can. I just don't have many office hours. But let me point this out because I pointed it out to the others. By the way, y'all divided up very nicely. I didn't count. I see 12 people. And I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. 3 on the team. Y'all did very well there. Okay. Huh? Yes, you did well. Excellent. Yeah. Okay. Yeah, let me go through page by page for folks who weren't here. Read the first page, that's page 15, and the top of 16. That covers part A and part B. But you'll notice at the end of B, there's number 6 has a bunch of white space. Now, when you were doing part A, or you're getting the data from someone else, you were filling out the table over on page 23, table 2.1, which was at the top of that page. And that was basically everything you need is in that table. Okay? Part B, you fill in the table down here at the bottom half of that page. But after you fill that in, then you go back to number 6 on page 16 and you answer the question there. But don't forget to answer the question. That's the point on the left. Then you did part C, and we actually did this in 3 pieces, and then we shared data among ourselves. And as you did that, you were filling in the data on page 24, data table 2.3. And then you got the others from the other people. And as you filled that in, you did as you read these 1 through 7, and number 6 and 7 tells you how to do the graph, which is on the back of page 24. Doesn't have a page number, but on the graph, so don't forget to do the graph. But as you were doing that, then number 8, number 9, number 10, and number 11 were all to be answered. 8, 9, and 10 based on what you did on part C, number 11 overall. Okay? Is that the last question you were talking about somewhere else? Keep going. Okay. Then we had results. You did the data, you made conclusions, you did what you needed to. Then you answer the questions on pages 19 and 20, 7 questions there on results. Some of this you get from your reading on the first page. Some of you get from what you did in the lab. Okay? And is it number 7 then that you're? The last number 7. Okay? All right. Then you had problems to do. And this is the only lab, I think, that's going to have problems at the end. So you have these to do too. And I explain what to do. So listen to the YouTube. And it's all in there. And I'm recording this too. I just have my computer turned in the wrong direction. But if you have any questions there, I'll try to answer those. But number 7, that's the one you're asking about, right? On page 21. Okay? What was your answer to number 6? 2.7 grams per cubic centimeter or somewhere thereabouts. Okay? And that's what it's referring to. In number 7, under what topic would you look in the index of a reference book to check your answer to number 6? What are we talking about there? What is measured in grams per cubic centimeter? Cubic centimeters measures volume. What is measured in grams per cubic centimeter? Density. Excellent. Density. That's where you would look to get that answer. Specifically, density of aluminum, because that's what you were dealing with. And if you check in the book, you'll see that's exactly what they record that to be. Okay? Now, do y'all need some more time to finish? Excuse me. Don't wake you up? Okay. To finish this lab, or you think you got enough that you can get it on your own? Okay, if you want time, this is a lab. You can work among yourselves with each other, help your partners out, that kind of stuff. Or if you think you've got it under control and want to take it home with you and work on it there, like I said, you have a week from today to get this in. You can have more time if you need it, but please Don't stretch it out too long. Get it in as soon as you can.
So a week for the day for this new lab?
No, well, actually for both of them. But for this one, you have a week from today because we didn't quite finish it last time. You asked a question today. If others have questions, I'll do it. If you finish earlier, I'll take them anytime. Like if you're finished with this today, I'll take it today. But if you have until a week from today, next Tuesday. Okay? The lab we do today, I imagine everybody's going to get everything they need today, and you'll probably turn it in before you leave because there's no results and problems to do with that one. You're just going to collect data, and you'll make some conclusions. There's a little bit on the front page. Okay? So y'all need some time on the first lab or not? Let me know. Okay. Okay.
I got a question.
Okay. Yeah, that's on results. Yeah. Describe, yeah. On page 19, number 3 under results. Describe what happened to the surface area to volume ratio for larger and larger cubes. Okay. This is again referring back to the part B, the data table 2.2. Describe what happens to the surface to volume ratio for larger and larger cubes. Okay, was that the part or the next part? Predict if this pattern will also be observed for other geometric shapes such as spheres and stuff.
Yeah, then explain the reason behind it.
What's that? Yeah.
Explain the part.
Okay. So here's the ratio. This is, as the cubes are getting bigger, you're going this way. What's happening to the ratio? That's really all you need to say. Which, by the way, since we're among friends here,
What question y'all
it was number 3 on page 19. Describe what happens to the surface to volume ratio, which is you look back on your data table 2.2, the one at the bottom of the page. The cubes are getting larger as you go from left to right, but the bottom entry, the ratio of area to volume, that ratio of area to volume, what's happening to that as the cube's getting bigger? Very good. Okay, the ratio, you can say it the other way, the ratio decreases as the cubes get bigger, or however you want to say that. But a little hint, since y'all are here, that doesn't differ too much from question 6 on page 16, does it? Isn't that almost the same question? The last thing you did in part B? Okay, so you see you get 1. Be sure you fill them in on both places. Yeah.
One more question.
Uh-huh.
Number 10 on page 18.
10 on page 18. Okay, got it.
I was asking you why you put it on.
Why you put the mass on the x-axis, or you put the volume on the x-axis and the mass on the y-axis.
Okay.
I put they were different units.
Okay.
And when you combine them, it's the average of both of them to get the.
When you did the slope, it was the ratio of rise over run.
Right, I understand that.
Okay.
Math
And
times
if you put- yeah, go ahead.
so the mass would be like the numerator.
That's the rise. Yeah, that's the rise, and this is the run. So you get mass per cubic centimeter, and that's going to give you velocity. So your slope of the line, your density, your slope of the line will give you the density in the correct units. I think that's what it was asking for. Let me go back and read the question. Density is defined as mass per unit volume or mass per volume. The slope of a straight line, yeah.
Why the volume was placed on the x-axis.
Yeah, so you would have that in the denominator, and you would have the mass in the numerator. That's it, exactly. Does that make sense? Good deal.
Mass would be the rise.
Okay.
Volume would be the rise.
Say that again.
Mass would be the rise.
Yes, exactly. So you get mass per unit volume. Exactly. Okay, any other questions? Good questions so far. I want to make sure those are all cleared up. When you have exhausted your questions, I can then start passing out. In fact, I'll go and start passing out the lab. I had left this to my work study student, taken it to be copied this morning, and then he forgot to go by and pick it up, and that's why I looked at, no, I have this yet, so I had to run down and get it on my bike. So here's today's lab. Sorry about it being so short. Okay. Get over it. Okay. You'll start complaining to the dean that I'm not giving your money's worth for the lab. Okay, I can hear you now. Griping and complaining.
So, what was the correct answer for the payment?
Say what you think.
I think the ratio of the skin amount on the potato and the weight should be the same. I would say that. Anyway, I think that'd be the same.
Okay. Well, what did your data tell you about the blocks? Is that ratio the same? Big block and little block? Huh? Okay, I see. Okay. Everybody got a copy of the lab? Okay. Now, I just did that to do something to kill time while you were working on the lab. Is that being worked? Oh, no, I've got one in the classroom. I'm going to get it. It's a real high tech one. I'm going to get it. It's not hard to get. I'm filling time while y'all are. Do not lose this pencil sharpener. I mean, this is very valuable. You don't know how much it costs. Okay. And there's a trash can over there. What's that? I don't know.
You want millimeters?
We're not doing that.
Ours like one of those mouse pad balls. It's got a rubber on it. It's got
Yeah, it is. You're exactly right. It is from the inside of a mouse. Okay. Okay. Do I take it that most people are through with their? Thank you. I was worried about that. Okay. Y'all are still working something?
The first lab, I got
First lab.
I got a few that I'm answering at home,
Okay.
but I'm gonna go ahead and get started on.
Okay. So if you want to get started, and a few teams I think have already started, what we have is the scales here. And let me explain to you what you can do with these. If you can get the ball to balance on the scale without rolling off, be sure you zero it before you put it on. However, if you have trouble keeping it on and you have to use a weighing pin, then zero the scale with the weighing pin on it. So all you measure is the mass of the ball. So I hope that's what the team did that did it. You got 3 balls: plastic, which is the ping pong ball; rubber, which is either looks like a rubber ball or it looks like the inside of a mouse, okay? And then the metal ball, that's pretty obvious what that is. So go ahead and determine the masses of the 3 balls. Be sure you zero your scale, either with the weighing pin on or off, but be sure you zero it before you take your measurement. Okay, am I recording? Yes, I am. Each one of the little bitty check marks is 1 gram on that scale. Yeah, every one of the little bitty marks is a gram. Because you see, yeah, 0 to 10 is 10 little bitty marks there. Okay, making fun of my. Okay. Okay.
Hey, where do you go off from?
Yeah, it was a gift from my grandfather, if you want to know. Okay. Okay, I already had it set up for 5. Yes, I did. You use the bottom, the longer one. I need to kick in my thing. Okay, I've already got your scale set, the inclined plane set up for 5 degrees. Okay? Okay. Let me go about the time. I see some people have already done it. Got to bung your stopwatch. You never got one. I had 3. Huh? I had 3. Because this one was this one that was beaten? The one thing on that with 2 stopwatches? There it is. Okay, Samuel was hiding it. He was going to try to rip it off. Okay. All right, stopwatches. The 10 o'clock button over here is, the 2 o'clock button over here is start, stop. Okay? Now, what I just did was 1.06 seconds. So the big number is seconds, and the little number is your decimal seconds. Your reset is over here at the 10 o'clock position. That resets it. Do not hit the middle button, okay? Because that's going to change the mode, and then I have to figure out how to get it back. I don't have the instructions anymore. Pain in the neck or some other body part. Okay. So, yeah, that's what you'll do next. Okay. Trying to get this so it won't alarm anymore, but I can't do it. Okay. All right. The second question is in measuring the groove. Okay. What you do here, pay attention to what Charles is doing here, putting this in against there and measuring against here and go to the nearest tenth of a centimeter. Measure in centimeters to the nearest. Hey, look at, yeah, if you're with this group, you can. You look at your own, okay? Measure from inside to inside. Inside here to inside there. Okay, good deal. Yeah.
Hey, what is it talking about here? Average speed, final speed, and average acceleration. How do I calculate that?
Okay, we'll get that later. Do your measurements first. Yeah, do all the measurements. Then we'll talk about calculations. Okay? Okay. Any questions so far? And by the way, for those who didn't hear me talking, when you're changing the angle, be sure you put the long side, the lower side on the angle, not the upper side, the lower side. One that sort of acts like a point. So when you go to 10, be sure, just like that's on 5, move that to 10. Is that what y'all been doing? Good deal. Good. I'm going to run down to my office and see if my work study student left me some papers. I've got to get them. And rather than leaving this running, I'm talking to this. They're taking measurements now. I forgot to tell them to do 3 measurements of each ball, each level, and throw out the high and the low and take only the middle value. So they're catching up on that now. Calculations. You took the middle time, you threw out the high and the low times. You had already measured the length of the track. That was in B, in centimeters. Divide that length by your time, all these various times here, that gives you your average speed. Okay? Once you got the average speed, then because it's uniform acceleration, the average speed was also the average between your initial and final velocities. So you add those two together, divide by 2. You're looking for final, so to multiply both sides of the equation by 2, the initial velocity is 0, which you put on page 1 under E. And then your final speed was twice the average speed. So what you got in the middle column, average speed, double that, and you get the final speed. All right. And when everybody gets those calculations done, we'll move on to average acceleration. All right. The last column on your data sheet asks for average acceleration. Can anyone tell me what the formula for average acceleration is? Average acceleration. Can anyone tell me? So again, I can't hear.
Velocity over time.
Okay, what velocity? Change of velocity. Change of velocity over the time interval. Okay? And what's your change of velocity? V final minus V initial over your time interval. I'll just leave the T or delta T. It doesn't matter. What's your final velocity? You just calculate it. Down the column. What's your initial velocity? 0 on every one of them. Okay? So it's just your final velocity divided by the time. So basically it's column 4 divided by column 2, or 5 divided by 3, whatever the final speed divided by the time. Final speed divided by time. Now I want an honest answer here. Did any of you predict that one of these balls was going to go faster than the other? The more massive, the less massive? What was your prediction? What's that?
I said that for the same.
Oh, well, they clever. Okay.
I figured the metal was because, like rubber, I figured it was going to friction on it or whatever, just the materials was slow down.
Did you see that come to pass?
No, I figured the rubber was going to be slow.
Slowest, was it? Actually,
It was our slowest we had yet.
what's that?
The rubber for us was the slowest.
On all of them, or just every now and then?
All of them.
Really?
The
Interesting.
Ours, the rubber, the more the rubber, and it seemed like it slowed down. Like at the end, our plastic actually slowed down.
Okay. I tell you what happens at the end, and y'all may not realize it, what you're probably measuring was your reaction time. Because probably it was so fast going down, you're just, how fast can you click the buttons? But, yeah. Was what? Okay, that's your quickest reaction time.
We drag racing.
Huh?
Like we drag racing.
Yeah. Okay. Sad news. Okay. All right. I'm going to, what we'll do on Thursday then, we'll continue in chapter 2 and do about 2.5 hours there, and then we'll do the second lab from chapter 2, which will be projectile motion. We'll get that far, I know, and then figure we'll probably get the books by Thursday, hopefully, and if so, then plan for the first test to be Tuesday, the last 30 minutes. We'll probably be pretty quick soon ready for the second test on Thursday, the last 30 minutes. So we'll try to squeeze some labs in between. So we'll see you then on Thursday.
Yes, sir.
For the whole time. Don't have to go to that thinking faculty meeting, right?
Is the door
It's still unlocked. Yeah. Thank you. Good deal. Thanks. Good deal. Thank you.
We gotta put the
Units?
units.
Good idea, too. And if you want to just put the top few and then draw a line down to get the bottom few.
Unit for time is centimeter squared.
No, time is in seconds.
Seconds. So that's just the S.
Got it. Chicago used to sing about that. All right, take care.
Gotta get these down.
Worthwhile lab?
Mm-hmm. And average speed.
Now our stuff is still here.
Okay, I'll get it.
We go average speed. Is that the
How do we do it? There's the formula on the board. Distance measured in. No, distance measured in.
This will be your length.
It'll be the average distance.
This will be the length of that thing that you measure.
Yeah. Cubic centimeter.
No, centimeters.
Centimeters.
Right, divided by time in seconds, so that'd be
Cubic centimeters per second.
centimeters per second, exactly.
I mean, I keep saying cubic centimeters. My bad.
Yeah.
Centimeters per second.
If you keep the units on a fraction, and cancel them out when you need to cancel them out, do whatever, you'll never get it wrong, as long as you keep it on a fraction.
I gotta get.
Units are your friends, right?
I gotta get used to doing
Because
it.
if you just write a number, don't nobody know what that number means.
Oh, that's your calculator. I'll say something about that.
We get some free time trial, man. We gonna go over that lab one.
Lab one?
Yeah.
Yes, a lot of questions on that one.
Oh, y'all would be asking more of them today, but you didn't.
I asked the one that I thought I needed to ask.
Okay. So
I ain't scared of that.
final speed is
Still a speed.
so it's gonna be in centimeters. Time. Hold on. That's still to be the same there.
How'd you get it? You just multiplied 2, which has no unit, by this, so same units as well. The speed is the speed is the speed.
So it's still the same.
If that ball was rolling for a few hours, then you do miles per something per hour. But we only did it for a few seconds, so you already know.
Yeah. Centimeters.
At least according to his clock.
Yeah.
Telephone, it was a few seconds. Yeah, I'm just kidding.
And we do average acceleration by.
And how do we get that?
I couldn't figure this one out. As soon as I get everything right.
You got speed.
Divided by time. This is in centimeters per second. Per second. Per second. Which would be centimeters per second squared. Okay. I'm going to shut this down.